Hello, in this video we're going to continue to look at some problems using cosine and sine waves, and especially looking at damping functions. And so in some physics problems you'll have a pendulum, some kind of a bob or a mass on the end of a pendulum, and the pendulum starts swinging to and fro. And as we know, it eventually comes back to rest in the middle. Just like if we have a spring, we can pull if we have a mass on the end of that spring, we can pull that mass down. And when we release that spring, it'll want to go upwards, and then it'll come back down and go up and down and up and down until it comes back to its natural resting place. And so we can use math to understand those types of damped motion problems. We've got a generalized formula here. Displacement, or the distance from center, or distance from initial resting place, as a function of time. That means that time is the independent variable, the x-axis, and d of t is y, or the dependent variable. And that's equal to ae of negative bt over 2m. A is our initial displacement, and negative b, or b, is our damping function or damping factor. M is the mass, and then we've got a period and a cosine function here. We're going to graph these out using GeoGebra. And you can imagine a long time ago, people had to plot out all the points, and going back even a few thousand years ago, men spent all day and their entire life just trying to do simple arithmetic and find out the relationship between the sides of a triangle, or something really sort of trivial or certainly tedious compared to, look at this, within minutes we can solve these really complex systems and complex functions. And so that's one of the benefits of technology there, that we don't have to spend our time plotting out all these points and making errors and having to adjust all of our calculations as we do trial and error type stuff. We can start to understand the larger issues and let the technology do the tedious stuff. So we want to describe the motion of the object. Be sure to give the mass and the damping factor. Again, our initial displacement is 15, and we can see down here at time 0 we have point A. At time 0, x equals 0, that's the time, and the displacement is negative 15. So we pulled that spring down, or we pulled the pendulum in what would be the negative direction. And so our damping factor is 0.9. T is time divided by 30. 30 is 2 times the mass, so our mass is 15, and we can also find that here in the square root. 4m squared equals 900. 4 times 15. 4 times 15 is 60. 4m squared. 15 squared is, what, 225 times 4 is 900. 15 squared, 225 times 4, 900. Yeah, and then 0.9 squared is 0.81. That all checks out. What's the initial displacement? Again, that's 15. Graph the motion. We've done that. What's the displacement at the start of the second oscillation? An oscillation is just one trough to trough, or peak to peak, depending on if we start up or down, start on the positive or negative. So we started on the negative, so the spring launched upwards and then came back downwards. So this is the start of the second oscillation. Each of these is an oscillation. And so we've got negative 12.53. We don't know what our units are there. What happens to the displacement of the bob? The bob is just the mass at the end of this string, or at the end of the spring, or whatever. As time continues on into infinity, well, we can see that even around 3-4 minutes, the spring or the bob returns to its original resting place. Okay, so again, with technology, we made quick work of what could have been a really difficult problem just even 20-30 years ago. It's really quite a luxury what we have today. So again, we can use that to help us understand the bigger issues, and then we let the machines do the simple stuff. We've got charging a capacitor here. We've got a very simple circuit: capacitor, coil, switch. So we've got V in volts across the capacitor, gradually diminishes to 0 with time. in seconds, and it's mapped out by the same type of function. Right, that's going to be another damping function. Oops, sorry, that's the sawtooth function. So here we have another damping function. This one is capacitor. Last time we had a spring or a pendulum. And we can start the capacitor. We can see the capacitor starts with a voltage of 1, right? 1 volt. It's very few volts. At what times t does the graph v touch the graph of e to the negative t over 3 and negative e to the negative t over 3? So we've got this upper and lower bound, and we can see the first part of the dampening function is just an exponential e to the negative t over 3. That's our top boundary here. Our lower boundary is the negative e to the negative t over 3. And so in the middle there, we've added a cosine function, and that's what gives us our oscillating motion here. So we've basically got exponential decay, limited exponential decay, or exponential growth, which over time, again, comes to a limit, in this case 0, which is the natural resting place, or 0 volts for our capacitor problem here. And so at the peaks and troughs, then our oscillating function touches those upper and lower limits. And when does the voltage V, when is the voltage V between negative 0.4 and 0.4 volts? I've got those points mapped out here. Right, at 0.35 seconds to 0.67 seconds, it's between those boundaries, and then again at 1.29 seconds to 1.75 seconds, and then everything after 2.19 seconds, it's between 0.4 and negative 0.4. So capacitor and spring or pendulum follow that same damping or oscillating damp function. Going on to the sawtooth problem. Sawtooth curve in oscilloscope displays a sawtooth curve. This can be approximated by sinusoidal curves of varying periods and amplitudes. And so we've got a series or a sequence of sine waves here. We've got 1 over 2 to the first power times sine of 2 to the first power pi x plus 1 over 2 squared times sine of 2 squared pi x. And we're going to add to that increasing values on the exponent of 2, 1 over 2 cubed, sine 2 cubed pi of x, and then we're going to add 1 over 2 to the fourth, and so on and so forth, increasing the value there of the exponent on 2. And so let me bring back up that sawtooth curve. And each time we do that, the sawtooth curve is going to get slightly rougher. It starts out relatively smoothly, as we see in green here. Right? It's almost like a sine wave. And then if we add one more value in our series there, it gets slightly rougher, and then if we add another value, it gets slightly more jagged, and then if we add another value, it gets even slightly more jagged. And as we carry this out into infinity, if we ended up with 1 over 2 to the 10th times sine 2 to the 10th pi x at the end of that series, then it would be quite jagged, and that's why we call it a sawtooth function or sawtooth curve, because it has all of these jagged points here, which relate to all of these different values in the sine curve there. All right, so let's look at another one. The displacement d in meters of the bob of a pendulum of mass m in kilograms from its rest position at time t in seconds is given by, well, it's that same damped motion function. And so I assume we're going to come up with the same questions. Describe the motion. Well, we know it's that damped function. So it starts, right? If it's a pendulum, we're going to start to the left. If left is negative and right is positive, sure. We're going to start at negative 15, so 15 meters to the left, and then it's going to move to the right, and it'll hit 14.45 meters, and then it'll move back to the left, it'll hit 13.92, and come back up to 13.4, and so on and so forth over time until it finally comes back to its initial resting place somewhere around 5 minutes, 6 minutes in there. What's the initial displacement? Again, 15. 15 to the left, if we call left negative. Oops. Sorry. Graph the motion, we've done that. What's the displacement of the bob at the start of the second oscillation? We've got all these points. And remember that, again, that cosine is what gives us our oscillating up-down motion like that. And if we just had the exponent, then we're going to get that limited decay, limited growth with a limit of 0 in the middle. And then our maximum and minimum values on our cosine function there just touch those upper and lower boundaries of our damped motion function. And what happens to displacement as it increases in time without bound? Again, it'll return to its original resting place. As you would expect, if your grandfather clock runs out of power, then the pendulum eventually stops moving. If you tie a ball onto a string, eventually it'll stop moving. It'll just come to a resting place. And so lastly, let's develop a model here. An object is attached to a coiled spring, is pulled down at a distance a 3 units from its resting place and then released. Assume the motion is simple harmonic with a period of t of 4 seconds. Develop a model that relates the displacement d of the object from its rest position after t seconds. Also assume that the positive direction of motion is up. Well, they don't give us any values for mass or the damping coefficient, and so this here is just this is with mass of 0 and no damping function. And we came up with that by inputting values of b equals 0 into this equation here. And so if we've got y equals ae to the negative 0 of anything, doesn't matter what that is, now it's 0. E to the 0 cancels out, that equals 1. So we got y equals a cosine times the square root. Remember our t equals 4 seconds, and so the period with simple harmonic motion, no damping. Again, if there's no damping, it's just going to be that cosine function. And so we've got 2 pi over w, or omega. Omega is equal to 4. This is squared, and we're going to subtract from that. Well, remember b is 0, so never mind that. And then we've got x on the back end there. So y is equal to, we can say, negative 3. If we're going to pull the spring down, negative 3 cosine, and then we've got a square root and a square. 2 pi over 4 is the same as pi over 4, or pi over 2, pi x over 2. And that's what it looks like. It's just a cosine wave without that damping coefficient. And we can see that the cosine wave is slightly different, right? It's flipped and then it's squashed along the x-axis a bit because we divided it by 2 and multiplied it by pi, or multiplied it by pi over 2. And so if we wanted to add something to that, we could add, if we wanted to add a mass and a damping coefficient, we could say that that's 3e to the, if you want to say the damping coefficient is negative 1, and we'll put x there, and then we'll divide that by 2 times the mass, 2 times, I don't know, 50, and then we're going to have to change this here, cosine pi x, let's do our square root, cosine square root, and then we've got, remember, 2 pi over 2 pi over 4. Oh, I lost it. E to the negative, well, we don't have to say 1x over, we say weight or the mass is 25, and so cosine square root 2 pi over 4 minus b squared over 4m squared. B squared is 1, so 1 over 4m squared. M squared, 25 squared is 625 times 2, 1250. And we'll put an x on the end of that. And what do we get? And so if we add a few values there, then we'll get that damping function again, same as in the rest. And we can come up with our upper and lower bounds by just taking that first part, the exponential function at the beginning. We can add that as another function here to get that'll be our lower bound. And then we can add it again for our upper bound by changing that to a positive, right? And we can find our points of intersection there, right? We can find our displacements at each oscillation. And we can see that over time that always ends up coming back to the initial resting place, or 0. And so we can see that damping functions are simply a cosine wave inside of an exponential decay or growth function where the limit is 0, and eventually, as you would expect, a spring or pendulum will always come back to its resting place. So too will this cosine wave always diminish and end up at 0 over time, as time stretches out into some value that's based on this damping coefficient here and the mass. Right? Thank you.